We're streaming.
Okay.
So I have a really cool new lighting setup that I've done, and it looks bad for you in the Zoom meeting because it's using my crappy
Yeah.
camera and it's not adjusted for it. But for the folks who are watching it live, it looks really good. The only problem is it's really hard on my eyes, so I don't think it's
Oh
the right
no.
thing to do. Yeah, I built a strip of LEDs all the way around my monitors, and so it's
Uh-huh.
you know, so I can do like a beauty vlog, right? But hey guys, but the problem is my eyes kind of hurt after doing an hour of
Yeah.
streaming, so I need to figure out a way to kind of soften the effect a bit. I think I'll put some kind of
So
like
what I
cellophane
was
over it or
looking to
something.
do and didn't do just because the lights I wanted to get were expensive was put a ring of LEDs around the back of my monitor that would reflect off the
Right.
wall at me.
The only thing I think is that you would then get this big shadow of the shape of your monitor. I've thought about doing that. Um, so we'll see. We'll see what I can do.
But you
Anyway,
can adjust the color of your monitor.
yes, but sometimes your monitor has things on it that have nothing to do with just trying to provide light to your
Yeah.
live stream.
No,
So,
that's true.
yeah. Larry Beckham sees the sunglass marks on my cheeks. Yeah. Yes, I am outside a lot in the summertime because it's so awful all winter long. And so the second it starts getting sunny, I am outside as much as I can. Except for when we have to do this stuff inside. But now we're about to take our hiatus. Now you know why we do it. So I can go outside. Of course, now I'm going to Australia in the wintertime. So much for that idea. Hello to a happy coder, Arnold Post, Astro B, Bill Sugden, Charles White, Chris Adams, Colin Jones, Deep Sky Dude, DPI 209, Frank Tippin, Ghost World, Gordon Dewis, Guido Bibra, Henrik Bo Anderson, Hugo Burnham, John Jacksish, John Suffield, Johnny Zed, Quad Libbet, Larry Beckham, Linda Sadek, Michael Meyer, Nancy Graziano, Nichols of the Yard, Nightbot, here to protect and serve. Paul Gracie, Peter Quinn, Arnstro, Rick Schwartz, Arjone, Sammy Kempainen, Susie Murph, Uncle Bill Druin, and Zapvan Zapvan. Hey, everybody. Hello. What? You all right?
I was muted to sniffle in the background
Mm,
because allergic reaction and sniffle.
I
Just
didn't even see that's what you were doing. Very strange.
and and I realized I don't have a disti on this computer and was trying to quickly install it before you noticed, but I failed.
Oh, caught you.
Yes, yes, you did. Yes, you did.
So while we're killing some time here, hey everybody, I just sent out my second email newsletter with my second, well, I've sent a pile of email newsletters, but this is the second one with a special question show just for you. Nobody else knows they exist. So if you haven't already, go to universetoday.com/newsletter and sign up to my cool email newsletter. I think you'll like it. And then I just dropped an episode we've been working on, and it was really hard, and it took us a long time, which was all about in situ resource utilization. So all of the cool spacecraft methods to gather space resources and turn them into things.
It's as hard to say
Yeah,
as to do, it feels like.
they need a new name then, and NASA's totally doubling down. Like the MOXIE is the Mars Oxygen in situ resource utilization something or other. So
Yeah. You need your vowels for your acronyms, make them pronounceable, and
right
in situ
in
provides you with an I.
yeah. All right, let's get cracking. So, one last little piece of housekeeping before we get on to this week's show. This is, of course, the final episode before we go for our hiatus. So, this is episode 498.
Hmm.
Yes. So, we will not be here next week. We will instead be. I'll be in Australia. You will. I don't know what you're going to be doing,
I
but
think I'm going to
enjoying
be
the
at
summer.
Archon next weekend.
Okay, there you go.
So any of you who are, it's not Archon, Alcon, any of you who are going to Alcon, should see me there.
Excellent. And then we will be doing the 500th recording in your hometown
Yep,
in September.
Edwardsville, Illinois.
And apart from that, we're both going to be kicking around. I'm going to be doing a bunch of stuff
Oh,
on my
yeah.
channel. You're going to be doing a bunch of stuff on your channel and on Twitch. So it's
Yep.
going to be a lot of fun. But at least we won't have this rigid schedule for 2 months, which is good.
Yep.
We won't have to go and find internet every time, once a week.
And did you hear we may have lower than normal viewers today because Comcast is out across the entire United States?
Oh no.
Yes. So, like, one of our largest cable internet providers in the US is down.
Oh, that sucks. And then the other thing, of course, is if you do want to hang out with some people over the course of the summer, I highly recommend join the weekly Space Hangout crew. Go to wshcrew.space. They are the awesome fans / executive producers / event organizers. They are our partners in all of the projects that we work on. And so if you want to be a part of that community, go to wshcrew.space and they'll hook you up.
And we're going to have all of our streams for CosmoQuest continuing through the summer. And so we've got your back.
Yep. All right, well, let's get cracking. You ready?
I'm actually going to go blow my nose before we go.
Sure.
It will be better for the long run. I
Oh.
will be right back.
Space stuff should have other cool sounding names like Blorb or Splurge or Schmeckles. Someone watches some Rick and Morty. Let's see. Thanks, Nightbot. So I think I'm going to be doing one more. And let me know how the audio levels are, because everyone always complains about the fact that I'm quieter than Pamela, and I've just got her turned down 7.2 decibels. I'm up 1 decibel. Hopefully we should be pretty close, but if we're not, please let me know so that I can just keep fine-tuning it until we sound about the same level in your head. I know this is the eternal. I can't hear you. Maybe you muted a thing.
Dotes
There
and
you go.
dozy dotes.
Yeah. That was weird. There's like a hissing noise coming from your mic, but
Really?
I'm sure it's going to be fine.
Okay. I am set up and ready to record and temporarily have clear sinuses.
Okay, good. Good luck with that. All right, I'm going to start the recording. Oh, there.
Hello, Chad. I have a head cold. I apologize for all the sniffling you're going to have to edit out. I am so sorry.
Oh, thanks, Chad. Astronomy Cast, episode 498, Dwarf Galaxy Update. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific, and the Director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. So we, people are sad, but we have warned them. This is the final episode before we go on to our hiatus. So of the season. So
we scared people last year.
I did that on purpose. So we're going to be away for 2. Oh, thanks, Green Shot. Anyway, we're going to be away for 2 months, July and August, and then we will be back in September. And we've got some pretty exciting things that are going to be happening in September. So if you have been watching, paying attention, we're all going to be coming together in Edwardsville in September to your house to have a big party.
Not entirely at my house. We're actually going to be spending September 15th at a brew pub, most likely. And then September 16th, we are going to be at the Wildey Theater. So yeah, this is something you guys can get out and register for now. We're going to have activities, maybe even fluid painting of tiny planets with me. Dr. Morgan Redberg is going to be joining us. And you can go register so that we can rent our spaces.
Right.
So to do that, to register and for more information, head over to astronomycast.com, go to the trips pull down menu and click on AC 500 weekend. Pre-registration is now open and requires a non-refundable $50 deposit. Again, we need to rent the buildings. Everyone who pre-registers, even if you have to cancel, will receive a goodie bag full of memorabilia from the weekend. You may pay the full $200 registration fee now, or you have the option of paying $50 now and paying the balance anytime between now and August 15th.
I can't wait to see all of you there.
Yeah.
And of course, during the summer, if you're feeling like you want to still keep the spirit going, join the weekly Space Hangout crew. Go to wshcrew.space. This is, of course, our fans, our producers, our friends, and they're the organizers of this event. They're the people who help us get guests for the various shows and sort of talk to each other about space while we are on our hiatus. So go to wshcrew.space and they will hook you up. All right, let's get on with today's show. So the Milky Way has gobbled up dozens of dwarf galaxies and added them to its structure. Today we're going to look at the ongoing hunt for the wreckage of past mergers and what we've discovered about dwarf galaxies in general. Dwarf galaxies.
Yeah.
A very actual fascinating topic of tremendous sort of scientific discovery in the last 10 years, and they tell us a ton about both the evolution of the Milky Way and really the development of the large-scale structure of the universe itself. So where do you want to start? What's new? Or
well,
what are dwarf galaxies before we
that's probably a good place
talk
to
about
start.
what's new with them?
And here I'm going to warn all of you. My master's research was actually on dwarf galaxies.
Dwarf galaxy
so
nerd.
Yeah, I admit to it. So dwarf galaxies have been known for a long time. They are these incredibly diffuse. You can look right through them in many cases. Tiny galaxies that are located in the spheroid around our galaxy and around many other galaxies. There are some freeform ones just floating around, hanging out between the galaxies, but the places they really are found is in these halos of galaxies. Like globular clusters, the smallest among them formed all of their stars during a single epoch of epic star formation. The earliest supernovas from this first generation of stars had such amazing shock waves that they actually were able to push all the remaining gas and dust out of these systems, leaving behind just lonely stars.
Oh.
Yeah, so they're cute. They're small. In our galaxy and Andromeda, they're found pretty much in the same disk as the rest of the stars and dust and nebula in our galaxy and Andromeda. And when we first recorded talking about these objects, we said things like they have the highest ratio of luminous to dark matter of any object that has been studied, and other things like that that are now entirely found to probably be untrue.
Oops. So can you go into a little more detail on that? Like, what did we used to think?
So it used to be that when we looked at these little tiny galaxies and studied the velocities of the stars within them, the velocities of what little gas we can see, we found that the velocities seem to correspond to these systems being made up of 99% dark matter and 1% regular everyday stuff that we can see and detect. And what's interesting is when we made these original assertions, we didn't screw up our observations, those were fine. But we based our calculations on the premise that let's just calculate it for the dwarf galaxy only and completely forget that the dwarf galaxy is like embedded in the halo of our own Milky Way galaxy. And that was slightly problematic.
Mm-hmm. So would you say that is now you've moved into the things we've discovered, the things that are new that we know about dwarf
Yes.
galaxies? So I think that, I mean, the biggest thing is just how many dwarf galaxies have been discovered here in the Milky Way. So, I mean, I don't know if you know how many have been found. I don't know if you have that number in front of you, but
No.
lots. What is the
Yes.
technique that they've really pioneered and used to find all of these dwarf galaxies?
Well, largely it's just counting stars that have similar composition and age. So as you look out with instruments like, or surveys like the Sloan Digital Sky Survey, Gaia, all of these large area surveys that have very consistent photometry and any spectroscopy at all allow us to say, hey, over here, there's a whole bunch of stars that have these characteristics and look like they could have all come from the same parent population. But oh, look, they form a stripe across the sky. Or, we don't have the ability to measure in detail the characteristics over there, but when we count the density of stars on the sky, what we find is there's a stripe of overdensity where there's a higher population than we would expect that is consistent with an arc of stars across the sky. So finding, well, shredded, tidally disrupted dwarf galaxies is now something of a sport for people working in these surveys. And I don't think we can get past a major scientific conference without another press release
Right.
on tidal stream from dwarf galaxy discovered.
Right, absolutely. That's one of the things. I mean, unfortunately, it's getting to the point where it's, like new planets discovered that we don't even report them anymore. And I'm sure back in the beginning, a galaxy found shredded in the Milky Way is a pretty exciting story, but now it's like, meh, whatever. Um, so but those are the ones that are, that the Milky Way has consumed in the past. And then, of course, there's the large and small Magellanic Clouds. There's other dwarf galaxies that are around us and just part of the local group. So, have you learned anything new about some of these? Not the ones that we've torn up and added to our mass.
So our discoveries fall into two different scientific groups of information. The first one was we initially thought that it was unusual and some weird fluke that the majority of the dwarf galaxies going around our own Milky Way galaxy go around the disk of the galaxy. Um, Andromeda has the same thing. We assumed that we were just weird because all of our models, all of our understanding of cosmology at this fine grained, don't have enough data yet level indicated, these should be randomly distributed around galaxies. And as we've gotten better data that has allowed us to see dwarf galaxies forming and existing around other systems, we've come to realize that no, they just tend to be in the planes of the galaxies they're associated with. And we can't explain this.
Because you would expect them to come in randomly from any direction, not to be nicely aligned in the way that they are. So, I mean, does that mean that they were spun out from the galaxies during the formation process, or does that mean that they were?
They weren't spun out. So that would imply that uh, as our galaxy formed, as it became the nice disky spiral that it is, globs of material got flung out like kids falling off of one of those spinny rides in the playground. And and that isn't quite what happened. But we have evidence in some colliding systems that as large galaxies collide, you can end up with tidal tails of stars that over time will coalesce into these dwarf galaxies. Now, it's unclear if that is the origin of all dwarf galaxies. It's most likely not, but it is the origin of some dwarf galaxies. And beyond that, we're just kind of confused. Now, there are things that we can look toward. For instance, it has been found in massive studies of the orientation of galaxies that formed out of the same cloud of stuff tend to share the same orientation, whereas when you look at galaxies as a whole, they have randomized orientations. It could be that these dwarf galaxies formed out of the same cloud of stuff as the massive galaxy formed. uh, we still have more modeling to do. It's still unclear. And this is why we keep doing science, to be able to answer questions like this.
Well, and one of the big goals of the James Webb Space Telescope, of course, is to be able to look directly out into to the really almost to the edge of the observable universe, to the time when these small dwarf galaxies were thought to be merging together into the larger spiral structures that we see today. So can we, what clues do we have right now about how these first building blocks were coming together back in the day? Oh, you're muted.
Sorry, we don't really.
Yeah.
This is one of the kind of awesome things about dwarf galaxies is they are so poorly understood. That seems like a strange thing to find awesome, but they're so fundamental, and yet they're so mysterious. And it's sort of like saying all of our food is made with flour and sugar, but no one knows where flour and sugar come from.
Right.
In this case, we have some people that think that, or theorize is a better way to put it, that dwarf galaxies are the leftover remnants of the cores of bigger galaxies that had the majority of the materials stripped off into the formation of galaxies like our own and Andromeda. There are people that think, no, these are just the primordial galaxies. This is how everything started out. And our Milky Way is made through the conglomeration of many, many of these tiny systems. We just don't know. This is where telescopes like James Webb, when and if it ever launches, are going to be so amazing, because they can look back with sufficient resolution to the early days of our universe and start to tell us exactly how did these things form.
So there's a couple of places I want to go. I want to talk about some of the classifications of dwarf galaxies that have started to come up. But one that's really recent news is this discovery of a dwarf galaxy that's almost entirely dark matter. Were you following this? That it's
Yes, but I don't know if we're going to keep that result.
Oh no, what?
So that was the other set of discoveries I wanted to discuss.
Okay.
So we initially thought that these things were, in general, pretty much all dark matter. And the way we got at that result was by measuring the velocities of the stars in the system, using the orbits of those stars to predict the total mass in the system, and then taking what can we see, that's the luminous, take what we can't see, that's the dark, and you get your baryonic matter to your dark matter ratio this way. Now, when we did those calculations, I did not do these calculations. I have nothing to do with this. When people did these calculations,
when the calculations were done,
they were done without taking into any consideration the effects of the Milky Way.
Right.
And it turns out, when you take in the effects of this giant galaxy sitting nearby, it kind of can lead to all of the motions that we see.
Right. But this galaxy, the one that I'm mentioning, this dark matter galaxy, was a little farther away, so it's not one that's that close to the Milky Way, and it was found. Oh, and I think it was by the motions of the stars in the galaxy that it had the mass of a regular or of a dwarf galaxy, but seemed to be comprised almost entirely of dark matter, and the stars that were in there were very old, and so it's the kind of thing that was incredibly surprising, but not outside the realm of what you might expect to see with a big enough sample size of the universe. That you're going to see every ratio from no dark matter to lots of dark matter, and they found one with the lots of dark matter.
So
they found one with no dark matter too, right?
I think you're talking about a galaxy that is normal galaxy massed, but has
Oh, you're right. You're right. You're right.
so it's with dwarf
Yeah.
galaxies
Yeah. Sorry. A
that
regular galaxy. Yes. Right. A spiral-ish galaxy found with almost no dark matter. Yeah.
yes,
Apologies.
exactly.
Totally should have saved that for the dark matter episode.
No, it's all good. It's all good. It takes multiple brains to try and put this episode together. Um, so it's it's turning out that when you do your calculations and include the mass of the Milky Way, you can get the observed velocities. Now, of course, there's people that are like, well, maybe. And so people are trying to find multiple ways to prove is there, isn't there, with the amount of dark matter in dwarf galaxies. And one of the is there, isn't there tests is to look at what happens to star clusters in the larger of the dwarf galaxies. So while the smallest are uh, just a few million stars that were all formed during a single epoch of star formation. So these are things like the Ursa Minor dwarf spheroidal galaxy. There are other dwarf galaxies that actually have globular clusters and other interesting objects within them and orbiting around them. By studying the orbit of a star cluster around a dwarf galaxy and doing kinematical simulations of, well, if you had enough dark matter to account for what we see, what would the effects on the star cluster be? If there's a really large distribution of dark matter, that's going to systematically destroy a star cluster over long periods of time. If instead what you're seeing is disruption gravitationally caused by our Milky Way, that star cluster gets to survive and actually grow over time. And guess which one of the simulations matches what we actually see?
The second one.
Yeah, the one with no dark matter.
Hmm.
So
Are
it's
you
looking.
like starting to like not be a fan of dark matter as its
Oh, no, no,
role
no.
to the
I'm totally a
formation
fan of dark matter. I'm
and
I'm just
and role on dwarf galaxies? That's what I'm getting
so
to.
its role in dark matter,
Yeah.
it's the role of dark matter in dwarf galaxies. I think we completely screwed up, and this delights me to no end.
See, people always say like, "Oh, astronomers, scientists, they don't like to be wrong, but they love to
Yeah,
be
no, we
wrong."
totally blew this one up,
Yeah.
and it's looking more and more like we do have ginormous dark matter halos, and these are what the large galaxies and superclusters of multiple galaxies all abide within. But smaller systems, the globular clusters, the dwarf galaxies we're finding, don't have these dark matter halos. And I'm just kind of loving this because it makes some problems much easier to explain and others harder to explain. And anything that gives a cosmologist a challenge that I get to sit back and watch and enjoy being an observer about,
Yep.
yeah, I'm good with all of that.
Now, there's some pretty fascinating kinds of dwarf galaxies that people have identified in the last decade or so and done a lot of observation. So I don't know how, I mean, I know you're a dwarf galaxy nerd, but things like the ultra compact dwarfs. I don't know if you did any research in like the most dense stars in a galaxy in the universe are these tiny little, they're like globular clusters on steroids.
Well, they're essentially transition objects between globular clusters and galaxies. And this is one of those things that leaves many of us just sort of like, okay, how do we explain all of these things? Because there's a lot of relationships that almost make sense with globular clusters being the leftover cores of disrupted galaxies, which is one of the things we brought up last week. But they're kind of missing black holes. It looks like maybe, but it's hard to look and see. Uh, then we find these ultra compact objects, and we don't know if they have black holes or not. And they seem to be another kind of transition object. And without knowing the full history of these objects, without being able to get good images of the early universe to see when did all of these different things come into existence, we don't know, are these ultra compact galaxies a transition between large elliptical and dwarf elliptical galaxies? Are they something entirely unique and have their own fascinating history? So this would fit in with the idea that globular clusters aren't cores of
Right.
galaxies and are instead formed in ultra dense high pressure regions. Uh, so dwarf galaxies and globular clusters are really the kinds of things you need to look at side by side. Uh, Ursa Minor has the exact same stellar composition as a globular cluster, but completely different kinematics. How do we get both of these objects? These are the things we can't figure out yet.
Yeah, I mean it's a great theory to say, oh, globular clusters are just the leftover cores because they kind of look like the
Oh,
core of a
yeah.
galaxy, after everything's been stripped away, but the part that kind of holds together is the core. And so all of those globular clusters that we see in the Milky Way, they're all just they are just leftover remnants. They're the pits of the fruit
Right.
that we couldn't eat. But and the one that's I think the people think is most likely is the Omega cluster, which is pretty
Omega
much
Sen.
the largest cluster in the Milky Way, and they think it has it has its own supermassive black hole at the heart of it, and it
It
really
has
has a lot of those
multiple
characteristics.
generations of star
Yeah.
formation. And so the question there is it actually a globular cluster or not? So we look
Yeah.
at things like M4, M13, these classic faint fuzzies you see in your northern hemisphere telescopes. Um, and they have this distinctive look, this distinctive stellar population. Omega Sen, how does it differ from these ultra compact dwarf galaxies that we see in other systems that we can't see as close? Is Omega Sen considered a globular cluster only because when it got labeled, we didn't know about the dwarf galaxies all that much yet? And is it like Pluto, where it just needs to be renamed as we learn more about it?
Yeah. We
This is
don't
basically an episode where I'm saying everything we thought we knew, we didn't.
we
And
didn't
isn't
know.
that
Isn't
awesome?
that awesome? I love it. Okay, so here's a question that we've been kind of arguing about a bit, which is the large and small Magellanic Clouds.
Yes.
Are they dwarf galaxies?
They are dwarf irregular galaxies, and it's kind of important to add these extra words. When we talk about a dwarf spheroidal or a dwarf elliptical galaxy, we're talking very specifically about these little tiny objects that the smallest have single epochs of star formation. They were theorized to have high dark matter ratios. They're now theorized to be totally excited orbitally by our own galaxy. Now, Ursa Minor, not Ursa Minor, the large and small Magellanic Clouds are bigger. They look more like a dead bug. They have the type of systems that you can't necessarily look straight through. I can show you a picture of a dwarf galaxy, and you will be completely oblivious to the galaxy in the frame because they are so diffuse.
Right. You can only tell by their movement of the stars all together to know that they are
Yes.
they are a thing that's together.
Yes,
Yeah.
exactly. And with with I'm going to keep saying the wrong one. With the large and small Magellanic Clouds, uh, you can just go
Yeah.
outside in the southern hemisphere during the right season, and they are there looking like someone took a fist of the disk of the Milky Way and threw it sideways. Uh, we see ongoing star formation in irregulars. We see supernova continuing to go off, for instance, 1987A. They're very, very different systems. So, dwarf irregulars, we're still seeing star formation, we're still seeing dust and gas. Dwarf ellipticals and spirals have settled out into standardized orbits for their stars. They've settled into spherical or elliptical shapes, um, and probably have a very different formation history.
And the second question, are they orbiting the Milky Way?
No.
Maybe. We don't. Again, I mean, I think if we'd asked this question, we would have gotten a bunch of answers back and forth. But they are in a gravitational interaction with the Milky Way, but not entirely certain if they're in orbit around the Milky Way or not. And
Yeah.
will they ever collide with the Milky Way? Maybe.
No.
We don't know.
Well, it all comes down to, again, a matter of mass. We don't know exactly how much mass our Milky Way has. We don't know exactly how much mass
Right.
these systems have. And uh, thus, we don't know escape velocities real well.
I mean, talk about a new sort of discovery right now. We've always said that Andromeda is so much more massive than the Milky Way, and now
Yeah.
it's getting closer and closer and closer that the two galaxies are very similar in mass. It's just that Andromeda has a much more massive, supermassive black hole. So was there any other sort of newish research in dwarf galaxies that you've been finding fascinating?
Um, so the loss of the belief that they had they had massive amounts of dark matter is really my favorite thing. There's a few smaller things. Folks are now looking to find the most pristine stars, the ones that have the fewest uh, heavy elements within them, within dwarf galaxies. And uh, we're using our understanding of the compositions of the dwarf galaxies to figure out how the composition of our own galaxy evolved over time. Uh, this being able to trace stars as they transition from dwarf galaxies to being consumed into our own Milky Way helps us understand the disparity between the composition of stars in different points of our own galaxy's disk. We're starting to build a picture, and it's a cool picture of how galaxies build up and change over time. We're just missing the first few chapters.
One of the things that's really fascinating that's coming up shortly, I mean, the Gaia mission has been gathering tons and tons of astrometric data about the motions of the stars through the galaxy. And it is the machine for
Yes.
finding these dwarf galaxies because, as we said, you're looking for stars that are all moving together in the same direction, either within the galaxy or even outside the galaxy. Um, there's a wonderful picture that came from Gaia that is a recreation of the Milky Way and the large and small Magellanic Clouds, but it's not really a photograph. It looks like a photograph, but it's actually data
Yeah.
from the spacecraft. And so this is just the most phenomenal machine for finding these kinds of objects. So I wouldn't be surprised, when the final Gaia data release comes out in a couple of years, that they are just going to turn up so many new dwarf galaxies, both the remnants, the tidal tail remnants inside the Milky Way, as well as the ones that are out there orbiting around us.
Gaia is one of the very few spacecraft I let myself get super excited about before it launched because it is just such an amazing piece of technology. And Godspeed, Gaia. Keep doing your job.
I don't think we've done an episode on Gaia. I've done an episode on Gaia,
It
especially about
it
the
came
new
up
data
in one of
release.
our planet finding
Yeah,
episodes.
yeah, but it's definitely worth us now doing a deep dive into Gaia
Yes.
because there's so many great results coming out of it. I wouldn't be surprised if it ends up being one of the most productive space missions ever launched. It's amazing.
Things to work on for 4.99
There
when
you
we
go.
come back from
Next
hiatus.
season. All right. Well, Pamela, as always, it's been an honor and a pleasure to do Astronomy Cast with you. I hope you have a great summer, and I can't wait to see you and all of the fans in Edwardsville, St. Louis, in September.
September 15th and 16th. And I can't wait for you to be here and to raise a glass in my favorite pub when there isn't a tornado going on.
Like never. All right. All right. We'll see you in September.
Bye bye. Now, don't go away. We're just saving our audio, folks. We'll take your questions in just a minute.
Quadlibet asks, any news about the Event Horizon photo?
Nope.
Spring
Nope.
2019 is what I've heard. Sorry.
So ridiculous.
That it's taking this long?
Yes.
Oh,
Because it's like taking as long as it would take for someone to get their PhD.
the Event Horizon telescope has to take its
No, no,
PhD.
no. So there's like when you're working on a research project, the timeline of the research project in general is, you can look at it in terms of how many PhD lifetimes is this project going to last. And when it comes to finishing one giant image, you don't expect it to take, it's like there's some poor graduate student somewhere who's responsible for all of this, and when they defend we finally get our data. This is not what's happening. This is just like where my
Right.
brain went.
Yeah. All right. Graham W. asks, have you heard anything more about the AT 2018 cow thought to be a supernova, except it's 10 times brighter in the galaxy constellation Hercules? Have you heard about this at all? No? So I've heard just a tiny little bit about this, that there's a new supernova was discovered. I mean, it's in the question. It hasn't, I haven't seen a lot of like papers written about it. I haven't seen any, beyond there was like this, the supernova network where people announced its discovery. And I've seen some people starting to talk about it, but there's no real, like, I mean, the way supernova happen, right, is it's kind of backwards from a lot of the research. The supernova is discovered, and everybody talks about the discovery of the supernova, but then it takes
We work
months, years for people to do all of the, they've turned all their telescopes on it, they're gathering as much data as they can, and then they're starting to make discoveries about what they've seen. And so we're going to have to just wait for probably a couple more months before the papers start to come out that'll tell us what they found and what they saw. So as you said in your question, super bright supernova, not really sure what it is, but it's weird.
And I'm going to mute again and blow my nose before we
Ew.
continue with the questions.
Tori Gadwa asks, is the mass of a supermassive black hole related to the mass of the galaxy? I'll start answering this question while Pamela blows her nose, which is that there is a relationship between the mass of the galaxy and the supermassive black hole that's in the middle of it, but there can be a range.
Not the mass of the galaxy, it's the mass of the spheroid of the galaxy.
Of the dark matter halo that surrounds the...
Not even that. It's literally the stars in the spheroid of the galaxy. This is where you can get disk galaxies that have no spheroid and thus appear to have no supermassive black hole in their center.
Okay.
It has to do with the formation of that spheroid is related to the formation of the supermassive black hole.
Arjone says, when the Milky Way spins, does it look just like a top, but the stars are actually moving random for the most part?
So they're not moving random. The stars in general are moving all in the same direction, all round and round the disk. So think planets in our solar system, except here, much bigger situation with many more objects. Now, where things get complicated is you have all of these different tilts and tips of tilts and things in the system. You do have the occasional things going backwards that were generally stolen from elsewhere.
Right.
The only time we get randomly oriented orbits is when we're looking at spherical things. So globular clusters have randomized orbits. This is what makes them round.
Mm-hmm.
If you have a disk, everything's going to tend to be going in disk-like ways. Now, when we look at a spiral galaxy and we see the various arms or the feathery structures that we call flocculent galaxies. Flocculent. It's a fun word.
No, I know. I can't help myself.
So in these systems, it's not that the arms are going in this high density area. It's that something happened at some point in time that led to an overdensity of stars in specific places. And as stars, so here's my arm in a galaxy. I'm trying to create a curve. There, we have a curve. As a star comes in towards this, they'll get accelerated into the high mass area, and then they'll get slowed down as they escape from the high mass area. This means that stars and other objects, gas, dust, whatever, will linger for a longer period of time within the arm structures. Right. And it's this building up for longer periods of time that give us the appearance of arms in systems.
Yeah. And so it's like all of the stars spend a little bit of time in the arms as these density waves
Yeah.
rotate around in the galaxy. And of course, as the density wave moves through, it brings the gas together. It leads to a bunch of star formation, which is part of why you see all these new stars forming in the spiral arms. But
Right.
but it is not, the spiral arms are not the turning stars of the galaxy. But they and so I mean, it's like, like those chairs that you sit on, when they go around, they go around and around.
Yeah, yeah,
It's
yeah.
like, you know what I mean, like an amusement park ride. Like that's what it is. And then people are at different levels as they go up and
Well,
down, right?
I think a better analogy to it is if you ever watch or experience stop and go traffic, especially where you have the looky loos on the highway when there's an accident or something just parked on the side of the road that's interesting.
Yeah.
They'll speed up to see what it is. They'll all get trapped in the traffic jam and then be slowing down to
Yeah.
look as they get to the end. And they're like, oh, okay, now I can just like fly forward. We're good.
Uh,
And so that kind of a density wave
yeah.
is the kind of thing that we encounter.
Right. And so when I think about like the motion of the galaxy, it is spinning like a top. One more analogy, like mix up a liquid with a bunch of like particles embedded inside of it, like bubble tea, and you mix it up, and they're all going to go around together, but they're going to be jiggling up and down, and they're going to be sort of
Yeah.
changing their heights, and they're going to be interacting with each other.
Hmm.
But overall, they're all kind of going around together. There you go.
Yeah.
That's the best we can do. Um, let's see. Okay, there was a question. Oh, here you go. So OBGYN Kenobi says, I'm a former student from roughly a decade ago. Just curious what your current research projects are. What are you working on?
Oh, all sorts of random stuff. Currently, we're trying to understand the difference in how amateur astronomers working on citizen science projects uh, are biased in what they detect compared to professional astronomers' biases. We're also working on developing photometry and astrometry software. I do a lot of support science, trying to figure out how to develop the software that will allow better research advances to be made.
Mm-hmm.
Uh, and this goes back to me really being an observational astronomer who attracts clouds.
Right.
So if I stay home and write software, no one has to be penalized for my cloud attracting skills. Um, as a side project, we're also currently looking at the ethics of citizen science. At CosmoQuest, we work a lot to make it clear you don't have to do any of the things you're doing. We will happily take your volunteerism. We will happily ask, can you please help us map out the moon, Mars, Mercury, all these things? Please help. We'll beg. But there's a lot of projects that actually have like students required to contribute, and they're not necessarily going to get uh, credit for what they were doing other than these classrooms. They're going to be underage. They can't really consent to giving their data over. What is the ethics of that? We see different places, including our own United States, that are starting to mandate doing more and more citizen science instead of funding the scientists to do the science as a cost saving measure. And what is the ethics of that? So I'm working with an ethicist
Wow.
where, yeah, it's super cool.
Astroethicist?
She's a science ethicist. She's a professor of philosophy, and ideas of consent, of coercion, all these different things. So, for instance, a ethical issue involving coercion is uh, what if you are someone who is told the only way that you can receive disability benefits is if you do volunteerism, and due to physical disability, you have to find volunteer activities you can only do online. And so your choices are basically citizen science or being part of like helplines and things like that.
Right.
Does that count as coercion? Are people being forced to give over data they wouldn't otherwise want to share? Um, so yeah, these are things that it's cool to think about, and I really don't want to do harm, by doing good scientifically.
Well, it's really nice of you to be, gathering together the work of many individuals and having a serious consideration about the ethical issues of that, as opposed to, for example, various social networks that just grind forward and don't worry about the ethical implications. So it's nice to do that.
Yeah, yeah. So
Yes.
we're trying to figure these things out. Yeah, so I work in multidisciplinary collaborations. We have psychologists, sociologists, an ethicist, software, and then of course all of the astronomers and planetary scientists.
So uh, Ghost World asks, do electromagnetic waves work exactly the same in space and other planets? Do the same effects of certain frequencies and their attributes hold true everywhere?
Yes. Now, this is with the caveat that an electromagnetic wave moving through a vacuum here is identical to moving through a vacuum there. Moving through oxygen on Earth, identical to oxygen elsewhere. Electromagnetic waves do change how they travel based on the material they're traveling through. Uh, this is actually something that's fun to check out with a cutting board that is made of like that milky plastic that you can still shine a light through. Get a pocket laser, the type you use to torment a cat, stick it into the edge of the cutting board, and you'll see the light hang a sharp turn. This is because of diffraction through
Right.
the medium. You can't see it, but it's also changing the velocity at which it's traveling.
Right. And so there are kinds of substances that it slows down light so much that you can walk around it.
Outrun it.
Yeah, you could
Rubidium gas.
yeah, you could shine your laser on one side of your tank of rubidium
Channel.
gas.
Yeah.
You could then run around to the other side and you could
Beat the
catch it
light.
and beat the
Yes.
light. And yet
Yes.
it's still moving at the speed of light from its
Through
perspective
rubidium.
through the medium of rubidium, which is just a mind-bending concept. So there are a couple of ways that you can move this faster than the speed of light, and one of those is if you handicap light and only let it move through rubidium gas. If we had a whole
Yes.
universe that was filled with rubidium gas,
It would
then
be very dense and collapse down before it ever evolved to the point of having planets.
right. But we could, I guess, but then there would be no vacuum, so we couldn't move faster than the speed of light. Anyway, there you go. Let's move on. Got another couple of minutes, so go ahead. Hit us with your questions. There was a couple of questions. I apologize. I'm going to have to go back. Quadlibit asks, an asteroid impact question. All of our data shows that impacts lead to large-scale cooling because of the sun blocking dust. Is it possible for an impact to do the opposite and cause warming?
Well, an impact, yes, yes. If you have an impact that throws enough material up, that material must then come down. And as it comes down, it will radiate its kinetic energy into the surrounding atmosphere as it's frictionally slowed. And that radiation of kinetic energy into thermal energy will heat up the atmosphere and toast our planet. This is actually probably what killed the dinosaurs, other than the initial shock.
Yeah, specifically catch all vegetation on Earth on fire simultaneously.
While just generally baking us.
Yeah, no,
So
but like it just lights. So it lights everything on fire
it's
at
the
the same
Fahrenheit
time.
451
Yeah.
problem.
Right. So you get to the point where the atmosphere is so hot that all flammable material
Spontaneously
ignites.
combusts.
Yeah. So is that global warming enough for you that the everything on Earth is on fire at the same time? And then of course you get the smoke and the dust and then you get your global cooling. So you get one then the other.
I would recommend a massive volcanic eruption instead, please.
Because then you just get the cooling.
Right.
Yeah. I know you're such a fan. I know you can't wait to usher in the destruction of all life on Earth from massive super volcano. Apparently they've found a new super volcano.
I don't know how I missed that.
Yeah, I forget where they found it. Apologies. I'll need to dig up the story and send it to you. And apparently, we might get a volcanic eruption in Canada. I think in the Rocky Mountains, because of global warming. So there's a volcano where it has a really big glacier on top, and that sort of is putting
Oh,
pressure on sort of the composition of the top of the volcano. And as the glacier melts and as that snow volume decreases, then it'll make it easier for the volcano to erupt. So
so what's interesting is I'm seeing two strains of news. One is new supervolcano brewing under three New England states,
there you
study
go.
says.
That's the one.
But then the other headlines are there isn't a supervolcano brewing under New England.
I didn't see that one.
So yeah. Oh,
Please continue.
okay. Uh, so yes, I want a supervolcano to go off, just not the one in Naples, not the one in Yellowstone, although that would be so awesome. But mammals. Because we haven't gotten to see one of these things as a science doing society. Um, and
Nor
we
do
can
we ever want
totally.
to. Look at Io. Don't worry about it. Um, Zappan asks, did I see Aya Yaya Yokel in Iceland? And we did.
Oh, and regarding the glaciation on top of the volcano that you have there in the Rockies, this is actually a known phenomena in Iceland as well, where they see that there is a statistical increase in volcanoes going off in the spring and summer when the pressure of the ice on top is released.
Let me try that again. Ayaf Yala Yokel. I got the yokel part. We had to practice how to say volcanoes. Yokel. That's volcano. It's the yokel part. Apology. Um, I still think you're one of the horse riders, horse people, horse,
Equestrians?
like the equestrians of the apocalypse. Yeah,
Or
the equestrians of the apocalypse. I think that's the good way to describe it. You
okay,
even like to ride a horse.
I do. I do.
So, Space TV asks, is it possible for someone to calculate the escape velocity of our galaxy? Yes.
But we have to know how much mass it has and the distribution of that mass because the escape velocity is a function of where you are in the galaxy, how much mass is internal to where you are, how much mass
Yep.
is external to where you are, and we don't fully understand the distribution of dark matter yet.
It's roughly 320 kilometers per second.
Locally?
Yeah, so in the
Okay.
direction of the solar system's velocity vector, you need another 317 kilometers per second to get it.
Okay.
Um, because the solar system is going 220 kilometers per second, if you're going from a full stop, say you're trying to escape from the supermassive black hole, then you need to be going 537 kilometers per second.
That that doesn't work for the galaxy. You'll actually have a completely different escape velocity in the center of the Milky Way because it's a distributed mass.
Right.
So,
So from our vicinity, from a
yeah,
full stop. If we suddenly canceled out our orbital velocity, then we would need 537 kilometers per second to get out.
yeah,
And escape velocity of the solar system is about 15 kilometers per second. Escape velocity of the Earth is about 8.5 kilometers. No, sorry,
no,
12,
thir-
11.5, 12 kilometers per second is
yeah,
the escape velocity of the Earth. So they're really big numbers, but they're
yeah,
not infinity. So some
no,
future
that's
civilization,
rockets.
yes. And also there are stars that have been kicked into velocities that are actually escaping the Milky Way.
Well, and we had a recent thought it was an asteroid. Now, no, it's a comet invader from another solar system that swept by last September, October. So we know that space invaders exist.
All right. Well, I think we've reached the end of our hour. Pamela, what's a thing that's happening soon that people should go and check out?
So tomorrow I will be on my personal Twitch channel, Painting Planets, and talking about how different compositions lead to different colorations and what we can learn about worlds just by looking at how they reflect light. So tune in to twitch.tv/starstrider at 4:30 Eastern, which is 9:30 London, 1:30 Pacific.
Awesome. And I just released my latest episode of The Guide to Space. Really proud of it. So check that out on my YouTube channel. Everyone, have a great summer. Pamela, have a great summer. I say it again. Join the Weekly Space Hangout crew. They'll keep you in space all summer long. And I hope we can see as many of you as possible at our live event. Dates again, September 15th and 16th, 2018 in...
And where can people find out how to see you while you're in Australia?
I'm going to be at Star Stuff, which is a convention in Byron Bay on July 7th and 8th. And I'm going to be giving a talk all about how we're living in the golden age of astronomy. Awesome. All right. Thanks, everyone. We'll see you next season.